r, meaning the distance vector, position vector from origin, and it is a vector meaning it is just a shorthand notation that it has 3 spatial components. You might say x, y, z or whatever. And then, of course, in dynamics and in electromagnetics, we have also time dependence there. Statics may be not time dependent, but then when we have radio waves, electromagnetic waves, there is a very important thing, is a quick variation of the fields. Antenna is radiating, meaning that the charges are, there is, for example, a spark, which is a very quick pulse and oscillation, which then generates the electromagnetic wave. So time dependence is important. And then, as you know, Maxwell's equations, I write them now here. So we have the curl of E field. Curl meaning this nabla, this del operation is perhaps something you know, I hope, and that is like a spatial vector differentiation operator. Sometimes in Cartesian coordinates you might say that del is, you have x component and the derivative to the x direction plus y component, and then of course z component. So we are using this so-called like Gibbs Heaviside notation of the vector fields. And of course you could have characterization of electromagnetic fields also in terms of tensors or differential forms or many other things. But this is perhaps the something that which is very useful to us. Well, I was writing the first Maxwell's equation, which means that the curl, the cross product of the nabla with electric field, every point and every time is exactly equal to the connected to the magnetic flux density and its time derivative, and there is a negative sign here, meaning that if magnetic field is changing, then the time derivative is non-zero. At that point there is a flux, the curl, like this kind of curly force to the electric field, and all the generators are based on this effect. So-called Faraday law or Faraday's law. You know, Michael Faraday was a great English scientist, 1790s to 1860s or even 70s. And this was 1831, his very famous observation about that magnetic fields has an electric effect, extremely important. And nowadays written in this form. Well, that is one. Then the other equation is similar, but that is to the magnetic field. Now H is the magnetic field, what we say, and that is again also a vector and dependent on R and T. But that is then more complicated, the right hand side, because there first we have the current density. Current, J means current, that is the how many amperes are flowing. This is like a field. This is not the total current that flows in a wire, but that is a differential thing. So in matter, if you are conducting matter, so say metal or burst conductor, there inside, if there is a current flowing, then point-wise there is a certain direction electron density. So this means that how many amperes per square meter and to what direction. And as in this form it is called so-called Ampere's law. And that was the famous finding by Hans Christian Ørsted, you know, the famous Danish scientist, 1820, who by accident found out that he had a Volta pile, you know, 1800. Volta, the famous Italian scientist, found out that he can have galvanic electricity by a combination of two different metals if he connected those by a electrolytic or liquid electrolyte, meaning that he could have galvanic current, which was not before possible, because before the electricity was static electricity, friction electricity, like sparks and so on. But then when he generated this kind of machine, then it was possible to make an electric circuit and electric current. And Ørsted found out that this current had magnetic needle, compass needle was turning in the vicinity of this current, meaning that if we have a current, then around the current there is a rotation in the magnetic field. You know the right-hand rule. You put your thumb to the electric current, the fingers show how the magnetic field is turning. But that is not the whole story. We also have the full equation also here, meaning that not only that kind of galvanic current creates the curl effect, but also similarly a so-called displacement current, meaning that D is now here the electric flux density. In vacuum it is about the same as the electric field. So electric field is temporarily changing, that also has the similar current effect to the magnetic field. And now you can see that there is a cross connection, electricity to magnetism, and then from here magnetism to electricity. And this is now already the idea that, okay, perhaps this kind of fields can be a part of electromagnetic field, which gives impetus to the next, and the next one is like walking with 2 feet, and then but walk very fast. Speed of light. Yeah. All right. And then, of course, D is also a function of space and time. Exactly. And then in Maxwell's equations, we sometimes also write the divergence equations. That the flux density, electric flux density is everywhere and all times the same as the charge density. This rho means charge density. How many coulombs in unit volume there is. If there is a positive charge, it means that there is a divergence. And you know, divergence is something that is flowing out of the volume. Opposite of convergence. If you have electron, there is a convergence because the fields come. There is a sink, and that is a source, a positive charge. And then finally, the corresponding magnetic divergence is 0. So you can see the very analogous thing between the electric flux density, magnetic flux density. Electric charge density, magnetic charge density is 0. So they say that there are no magnetic charges. We have magnetic sources, certainly, have a strong magnet, permanent magnet, and which that creates a very strong magnetic field. But the fact is that there is no charge density, because that is a dipole, very close plus and minus together, so that you cannot separate those. You try to make a magnet, you take 2 new magnets. Except a couple of weeks ago in Nature, do you follow the journal Nature? There was, let me see, this kind of article. So have you heard about this journal, Nature? This is in October 15th, 2009. Measurement of the charge and current magnetic monopoles in spin ice. Monopole is not a dipole, but that is like a point charge. They say that in spin ice there would be magnetic monopoles. I tried to read the article, but I didn't understand anything. So, but I urge you can perhaps read that, yeah. Well, but you